right, so today we're going to have a brief little lecture on weak acid mixtures and polyprotic acids. They kind of go hand in hand, so let's take a look at them. First, let's talk about weak acids. So whenever you throw more than one acid in, there's usually one that's going to be dominant, and that dominant one is going to produce pretty much all of the H pluses. If you had to worry about every single acid, if you had multiple acids in a container, and how much each one produced and add them all together, it would be a nightmare because they'd all be messing with each other's equilibriums. So here's what we're going to assume. We're going to assume that the amount of H plus produced from all of the weaker acids is nothing compared to the amount of H plus produced by the strongest one. And then we're going to use that H plus to solve the rest of the problem.
Okay, I'm going to talk very briefly about what happens if you have a mixture of weak acids. Typically, we've been dealing with only one acid in a problem, but what if we have two or more in a problem? The good news is there's no problem as long as the Ka values are really different from each other. See how we have, in this case, we're going to dump into a container, we're going to dump in both HCN and we're going to dump in HNO2. Now, the nice thing about it is that HCN has a Ka of times 10 to the negative 10, which means it's really, really weak. HNO2 has a Ka of 4.0 times 10 to the negative 4, which means it's significantly stronger, to a factor of 6 places, right? So it's about a million times stronger. Now, the nice thing about this then is if we're trying to figure out how much H pluses are in the solution, we can assume that the HNO2, because it's so much stronger than HCN, is the primary source of H pluses. And if you take a look at the two equations here, the HNO2 produces H plus and its Ka value is this, whereas HCN has its Ka value right here. So all we have to do is solve for the H plus for HNO2. And so if we do that, we have the equation already written. We can write HNO2 goes to and comes back from H plus and NO2 minus, yeah? They're all aqueous. And if we want to do an ice problem with this, which we can, we start off with, in this case, 5.0 molar HNO2. So we have 5.0 molar of this, actually it's 5.00 molar of this, 0 and 0 of this, and we go into our regular ice mode. We go minus x here, plus x, and we have at equilibrium, we have 5.00 minus x, and here we have x and x. And if we plug it into our K expression, our Ka expression, which would be H plus times NO2 minus, and put that all over HNO2. I'm not a big fan of the fact that they did not put plus H2O over here like they normally would in a problem, but aqueous means the same thing, and H plus is the same thing as H3O plus. They're both the same thing. So if we plug it back into our Ka expression, we end up with x times x all over 5.00 minus x. The nice thing about this is that this goes bye-bye because of the 5% rule, and that's all equal to 4.0 times 10 to the negative 4. Now, if we then solve for x, which I've in advance gone ahead and done, the x value is going to be 4.5 times 10 to the negative 2 molar. And what that's equal to, and this is really important to add in here, it's equal to our H plus concentration. So if we then want to figure out what our pH is, because that's what we're doing, wouldn't it just be the pH, wouldn't it just be the negative log of our H plus concentration? And if our H plus concentration happens to be this, wouldn't it be the negative log of 4.5 times 10 to the negative 2 molar? We do the math on this, and the pH of the solution ends up being 1.35. Notice we do not have to worry about our HCN at all in that. Now, they did, however, ask us to figure out the Cn minus concentration. Now, if I were to write the equilibrium expression for the Cn minus, I'll use a different pen so you can visualize this a little bit better. The Ka for that, wouldn't it be equal to my H plus times Cn minus all over HCN, and wouldn't that be equal to 6.2 times 10 to the negative 10? Now, we could do a whole ice problem here, but one of the things you need to be aware of is this. We know what the Cn minus concentration is because they tell us in the problem that the HCN, not the Cn minus, HCN is 1.00 molar. So we know what the concentration is down below here at equilibrium. The H plus concentration, see this amount right above it? That's the H plus that we got from the HNO2 dissociating. So that means that that H plus amount is going to be sitting in the solution when this starts to try to dissociate. So this HCN is never going to produce as much H pluses as already in the solution. So at equilibrium, the amount of H pluses from the previous dissociation are going to be sitting in here. So when we plug the numbers in, we're going to have 4.5 times 10 to the negative 2 already here. We are trying to solve for Cn minus, and we know what our Ka value is, and we know what our HCN value is, which is 1.00. And when you do the math on that, by the way, that's all equal to 6.2 times 10 to the negative 10. When you do the math on this, what ends up happening is that your Cn minus concentration ends up being equal to 1.4 times 10 to the negative 4 molar. So the Cn minus is equal to this. Now this is a kind of a snapshot on this. We can go more in depth on this, but the cool thing about it is that anytime you have a mixture of acids, you can always figure out the pH from the strongest of the two acids, and then the amount of H plus that you get from that original acid can be used in the equilibrium problems of any of the other acids that are in this problem.
Okay, so now we're going to talk about polyprotic acids, and they are, in essence, we're going to treat them exactly like weak acids. What is a polyprotic acid? Well, it's when you have an acid that has multiple hydrogens, and what we do is we pull one hydrogen off at a time until we get to the final juicy core. It's kind of like those babushka dolls where you open them up and you finally get to the center. We get to the smallest or the conjugate base that's left over. Now, just like we did with mixed acids, whenever we have like something like H3PO4, which is the example we're going to use, we have 3 hydrogens there that we can pull off. So the first hydrogen that we pull off is going to produce so many more hydrogens than the other 2 combined that we can assume that all of the hydrogens come from the original dissociation step. So let's take a look at a problem, because that's the best way to do these. And in this case here, we're going to say calculate the pH of 5 molar H3PO4 as well as H2PO4 and HPO42 concentrations at equilibrium. So our first thing, as we always do, is we want to write our equilibrium expression. So we're going to go H3PO4, and what are we going to do with this, I wonder? What's the only thing we can do with it? Throw it into water, right? So we're going to throw it into water. And remember, in this case right here, this water is acting as a base. So it's going to grab that hydrogen. It's going to form H3O plus, which we know as H plus. And left over is going to be H2PO4 minus. Now, they've given us in this problem the initial amount of, we're going to do our little ice table here, of 5.0 molar of this. Now, since we're just starting with this and we're throwing that into water, we're going to have none of this and we're going to have none of this to start with. Again, this is a 1-to-1-to-1 ratio, so we're going to lose x here, we're going to gain x here, we're going to gain x here, and then at equilibrium, we're going to have 5.0 minus x, x, and x. Now, as always the case, we've got to write our equilibrium expression. So we're going to write this Ka. Now, I don't know if you can see here, but there are 3 separate hydrogens and 3 separate Ks. And do you see how it goes from 10 to the negative 3 to 10 to the negative, and my eyes are really bad, negative 8, I believe, and then 10 to the negative 13. So we're going to use the first K, and we're just going to call it, ironically, Ka1. Now, I'm going to move this over just a little bit so we can have a little bit of space. But if I write Ka1 here, would that not be H3O plus times H2PO4 minus all over H3PO4? This pen seems like it's giving up a little bit, so I'm going to switch over. Now, we're going to put all these values in, and again, some of you may find it tempting to just jump this step, but they're going to have x times x all over 5.0 minus x, and that's going to be equal to our Ka in this first step, which is 7.5 times 10 to the negative 3. We're going to 5% rule this, so we don't have to worry about it. And then when we do the math, it's going to be this, 5.0 times 7.3 is going to be equal to x squared, right? So x squared is equal to 7.5 times 10 to the negative 3, all times 5.0. And if we take the square root of both sides, we're going to end up with x equal to, and I've done the math in advance, 1.9 times 10 to the negative 1. Now, if you are a purist and you're like, I hate writing exponents, you could write that as, shift it over, couldn't you, and go 0.19. And that x, that's equal to our H plus or our H3O plus concentration. Now, that's important because if I want to solve for the pH of the entire thing, we're going to assume that this H plus dominates all the other things that are in that solution. So if I want to take the negative log, which is what pH is, it'd be the negative log of this 1.9 times 10 to the negative 1, I'm going to end up with a pH of 0.72. Now notice here I'm using two significant figures after the decimal because we use two significant figures here and two significant figures here. Now, what does that lead us to? Well, that leads us to our next step, because once we've completely gotten rid of the hydrogens, the only thing that's sitting in there right now is H2PO4. Now, we're going to talk later about how this H2PO4 theoretically could go back this direction, but the way we're working it here, the H2PO4 still has two more hydrogens that it can lose. So we're going to pull off the next one. Now, one of the things before I do that is, if you take a look at the question, it says, what is the concentration of what is the pH, and what is the concentration of H2PO4 as well as H2PO4 2 minus? Now, can you take a look here, and you see how the H plus concentration and the H2PO4 concentration are the same? So this is the same as the H2PO4 minus concentration as well. So we already have the answer for the first one. But now what we're going to do is we're going to start with this, and we're going to again throw that into water. And whenever we have multi-step acids, we always take care of the first hydrogen until it's completely gone, and then go to the second, third, etc. So how does that look? Well, we take our H2PO4 minus, and what do? When in doubt, throw it into water, right? So we're going to go plus H2O. And what we're going to get is this hydrogen leaving and joining here and forming H3O plus, which is just our code word for H plus. And then we're going to be left over with HPO4 2 minus. Now, this is important because in this problem, the second part of the problem says how much HPO4 2 minus is there at equilibrium. Now, what are we starting with here? Well, the H2PO4 minus that we're starting with is equal to our X value that we had in the beginning, right? So we have right now 1.9 times 10 to the negative 1 of this as our initial. I'm going to do ICE. This, again, we don't care about. Our H3O plus, do you realize, is exactly the same as this, because that's what we had in the first step. And the H plus that this is going to generate is so little we don't even care. So it's going to be 1.9 times 10 to the, again, negative 1. And over here is the only thing we don't have to start off with, which is 0. What's going to happen? We're going to subtract x here, we're going to add x here, and we're going to add x here, leaving us with 1.9 times 10 to the negative 1 here, 1 minus x, 1.9 times 10 to the negative 1 plus x, and x. Now I'm going to rewrite our equation over here, and as I'm erasing this, you may get a glimpse of what is going to happen next. If you write out your Ka2 for this, won't you end up having this on the top? Won't you end up with H3O plus times our HPO4 2 minus? And by the way, isn't that what we're trying to solve for, right? All of that's going to be over our H2PO4 minus concentration. Now, I don't want to spoil this for you, but do you see how the H3O plus here is 1.9 times 10 to the negative 1 plus x, and this is 1.91 minus x? But in both these cases, I'm going to do the 5% rule over here just so you can see how easy this is to do. I can get rid of both of those, and doesn't that mean, therefore, this, that the 1.9 times 10 to the negative 1 for the H plus on top, and the 1.91, or 1.9, not 1.91, times 10 to the negative 1 on the bottom, they're going to be equal to our new Ka. And this time it's going to be Ka2. If we look up on our table over here, we have 6.2 times 10 to the negative 8, 6.2 times 10 to the negative 8. And according to the wonders of mathematics, won't it be just this? So won't our x then be equal to 6.2 times 10 to the negative 8? And our x in this case, isn't it equal to our HPO4 2 minus concentration? Now this is a really happy spot. When we start dealing with titrations later, I'm going to find a place you can actually see my face. When we start doing titrations later, this is called the half equivalence point, but we're not going to deal with that right now. What we are going to be excited about is we have HPO4 minus's concentration. Now, there's still a hydrogen here, right? So if we wanted to, we could rip that hydrogen off and do the same thing, except we'd be starting with HPO4 right here, and over here we'd end up with PO4 3 minus. What value would we put for the HPO4? Well, this value we just got right here. What value would we put for H3O plus? Well, the one we've been using from the very beginning. And that way you could solve for the HP or the PO43 minus. I don't feel like going through this step, but if you want to take a look in the textbook, they do that step. Hopefully this has been helpful. We'll go over more of this in class.